So, number one. So number one, hopefully you remembered this one. If I differentiate this, so number one was to differentiate this. And if you're looking at this video, you might like to pause it and have another go at it and remind yourselves of it. The rule we're applying is, and if you, after a while, when you've done a few, you can just remember it. All you do for these sorts of functions is you bring the power down and times it by the number in front, so 4, 3 to 12, and take 1 off the power, so 3 minus 1 is 2. So it's easy, 12x squared. But it's only easy when you've done a few. And you might also remember that the differential of a constant is always 0, so that disappears. So the answer is just 12x squared. So hopefully you got that right. That's what we were doing last year in Unit 4, this sort of thing, differentiating straightforward functions like that. The second question is just a reminder, if I do go to all the trouble of differentiating a function, well, there's a point to doing that because it tells us something about the original function. And what's that? The gradient, right, the gradient of the line, or the rate of change. How is that function changing, the rate of change of y with x, whatever that is? So the differential tells us the gradient or the rate of change. And if you think of the assignment 5 that you're doing, you've been asked to differentiate functions and then plot them, and then you can see what the gradient is at a particular point, because that's what the differential tells us. Number 3 was to look at this velocity time chart and think about what the gradient of that line is. So if I differentiate this function, I get the gradient. But what does that gradient tell us, and what does the area underneath the graph tell us? So what does the gradient of that line tell us about the movement of the object? Yeah. It tells you the acceleration, exactly right. How is the velocity changing with time? And that's what we call acceleration. Talking and writing at the same time. Acceleration, the rate of change of velocity with time. Because this is a straight line, what does that tell us about the acceleration? Right, it's increasing at a constant rate, yeah. So whatever that acceleration is, say 3 meters per second squared, the gradient was 3 in other words, that's not changing, it's a constant acceleration. So I could have a situation where I've got a curve, some sort of function like that, and I could still find acceleration by differentiating it, but now the acceleration is constantly changing. Any ideas what the area underneath the curve tells us? Yeah. Tom. Good. And to work that out, if I'm going at, say, a speed of 5 meters per second for a time of 3 seconds, what does the area tell us? It's velocity times time. If you think about area, it's the units of velocity, which is on this axis, multiplied by the units of time. I multiply them together to get the area, don't I? So actually, if you're not sure, all you need to do is multiply the units of one axis, speed, by the units of the other axis, time. They cancel, and you're left with meters. So whatever I've got, it will be in the units of meters. So that's distance, as Tom says. So the area underneath there tells us the distance. And as we'll see, the area underneath the curve, to find it, if it was a straight line, well, I could find that. I could divide that into a rectangle and a triangle, work out the area. But if it's not a straight line, if it's a curve, then it wouldn't be straightforward. And in fact, when we do integration, we'll be discussing that integration is a way to find the area underneath the curve. So that's where integration comes in, and we're looking at that today. So if I wanted to find out how far this thing had gone, I'd get this function and I'd integrate it. And that would tell me how far it's gone. And similarly for this. What does the gradient of a force against extension graph tell us? If you've done this in mechanical principles, you would have found what about the material? Sorry? Change in? No, that's... Oh, sorry, who's speaking? I can't see. Right, okay. Change in length. Now, that's this axis here. If I found the gradient of that line, what's it to do with? If this gradient is steep, what's it telling us about the material? In a way, yeah. Look, big force, small extension. If the gradient is small, small force, big extension. So what does the gradient tell us about the material in a way? The modulus of elasticity, Young's modulus, okay? How stiff the material is, how hard it is to extend it. And you've probably done this, haven't you? You've worked out Young's modulus by finding the gradient of the line. We could do it for any function. If I knew what the function of this line was and I differentiated it, that would give me Young's modulus. Area underneath the curve. If you think about what we did on the previous example, what was the area? It was the units of velocity multiplied by the units of time. This is the units of force multiplied by the units of distance. So whatever it is has got the unit Newton meters, or force times distance. What is it what's the formula that involves force times distance? Energy stored, right, good. Or work done. Work done is the area underneath the curve, or energy stored. So if I were to stretch something, then that's how much energy is stored in it, in a spring, say. So if I release that spring, that's how much energy has been released. Or I can calculate how much work is required to move it from there to there, say. Find the area underneath the curve. Okay. Finally, integrate this. Anybody have a go at it? Paul? Yeah. Right, good. Excellent. What we do is we take our 12x squared, add 1 to the power and divide by the new power, you might remember from last year. So we get 12x cubed over 3, which comes to 4x cubed. But then we have to add something at the end. Can you remember what that is? Yeah, we add c, this constant of integration. Integration is the opposite of differentiation. So if I want to check I've done that right, and you may have noticed actually that this example is the exact opposite of the first question we had here. If I differentiate 4x cubed plus 3, I get 12x squared. If I integrate 12x squared, that gets me back to the original function, 4x cubed. But the trouble is, I can't get back to the 3 because when I differentiate, that's gone. And if you remember from last year, all I can do now is say, well, plus c, some constant, but I don't know what that is. And today we're going to be talking about how you find out what that constant is for a particular situation. So that's our introduction to the ideas of why we're going to do what we're doing today, integrate these functions.